YouTube channel. All right, Chemistry 102, continuing on with our final exam review, questions 11 through 13. You're asked to name some molecules. We have two alkenes and an alkyne. Well, the first alkene, what's the first thing we're going to do? We're going to find the longest carbon chain, which is pretty obvious because it's only one chain, but we're going to number it from the end such that we give the double bond the lowest possible number. So 6, 7, 8, 9, 10, 11, 12. So you might remember that after decane, so you have decane. Then when you add a carbon to that, 11 carbons, you have undecane, and dodecane. Now, I don't think I have anything about dodecane on your exam, but it's just a little reminder for you. So this is some kind of 3-dodecane, and you can see that the two hydrogens are on opposite sides of the double bond. And so this molecule would be trans 3-dodecane, trans 3-dodecane. If I look at the other one, the next alkene, it's pretty quick to name this one. We have 1, 2, 3, 4 for our longest carbon chain. The double bond is on the first carbon, so this is some kind of 1-butene. And I have two methyl groups, both at carbon 3. So this would be a 3,3-dimethyl 1-butene. And keep in mind there's no cis or trans here, because whenever you have two substituents at the end of a double bond that are identical, there is no such thing as cis and trans in that case. All right, let's move on to the next one. We have a triple bond. We want to find the longest carbon chain, and we want to number it in such a way to give the triple bond the lowest possible number. So that would look like this: 1, 2, 3, 4, 5, 6. So this is some kind of 2-heptine, or 2-hexine rather. Now I have a 1-iodo substituent, and I have a 4-methyl on my 2-hexine. So how would I put all that together? Well, I is going to come before M. And so when you put all that together, you get 1-iodo, 4-methyl, 2-hexine for our alkyne. All right, the next one is just drawing a structural formula. The molecule that we want to draw is 2,2,4-trimethylpentane. So I always like to start with the parent carbon chain. It's a pentane. So we have 1, 2, 3, 4, 5, like this. If we number the carbons, this would be carbon 2, this would be carbon 4. On carbon 2, I have 2 methyl groups like this, and on carbon 4, I also have a methyl group like that. And there you go, done. So I always find it's fastest to draw structures when I use bond line formulas, right? You can draw them very quickly. All right, next one, it says, which would you expect to have a higher boiling point? 2-methylbutane. So that would be 1, 2, 3, 4. This is 2-methylbutane. Okay, or pentane. 1, 2, 3, 4. Well, if you think about the only kind of intermolecular forces that these molecules will experience would be dispersion forces, right? Because these are hydrocarbons. There are no polar bonds and there's no opportunity for hydrogen bonding. So if you think about these two molecules, if I had another molecule of 2-methylbutane, if I just draw it like this, you can see how much less efficient the packing is here compared to what if I had another molecule of pentane. You can see how, since this is completely linear with no branching, that the packing is highly efficient. And so the intermolecular forces represented by the yellow highlighter are going to be maximized. And therefore, the pentane, maybe I'll just write it up here, is going to have the higher boiling point based off of the increased dispersion forces. And you have to understand the difference between dispersion forces, which are the same thing as a London force, right? You have to understand a dipole force or a dipole-dipole force, and you also have to understand hydrogen bonding. Now, again, in this question, the only one that you need to consider are the dispersion forces, which are stronger in the linear or non-branched molecule pentane. Question 16, draw the possible products that form when the following molecule is dehydrated in the presence of a strong acid and heat. Label the major product, the Zaitsev product. So you know that when we do an elimination of water by taking a secondary alcohol like this, it says a strong acid and heat. So we'll just put H+, concentrated strong acid, and we'll put the triangle, which represents delta or heat. Well, what we're removing is we're going to end up losing H2O. Where's that water going to come from? Well, one of the hydrogens in the oxygen is going to come from the alcohol. Where's the other hydrogen going to come from? Well, there's two possibilities. This is an alpha carbon, this is a beta carbon, and this is a beta carbon here. You see the beta carbons in red and blue are different, aren't they? If I remove the hydrogen from the beta carbon that I have highlighted in blue, I would end up with this compound. And if I remove the beta hydrogen from the carbon that I have highlighted in red, it's going to look something like this. Okay, so if I examine those two double bonds, which one of them is going to be the Zaitsev product? Well, if you look at this double bond, this one is tri-substituted, and this double bond is di-substituted. The more substituted alkene is going to be the major product. This is going to be the Zaitsev product, which is the major product. Major product. This compound is called the Hoffman product, and it is going to be the minor product. Question 17, draw the possible products that will form when the following molecule is reacted with hydrochloric acid. List the major product of the reaction. Well, here we have an example of Markovnikov addition, right? We have HCl, and we have an alkene that isn't symmetrical. What do I mean by non-symmetrical? It means that this carbon is different from this carbon, right? The carbon on the right has a hydrogen already attached to it. The carbon on the left has no hydrogens attached to it. So what's going to happen is the rich will get richer. The carbon that already has the hydrogen, that's the one that's going to take the other hydrogen. And that means that this carbon is going to take the chlorine. Let's draw what that would look like. I'm going to have the two carbons from my double bond. I'll have this methyl group down here. This methyl group here, I'm going to have a chlorine on this carbon now, and then I have my 1, 2, 3 carbons like that. So this is a Markovnikov addition of HCl across a double bond, and you have to know the Markovnikov rule. The rich are going to get richer. The carbon that has the most hydrogens on it, that is the one, if we highlight the hydrogen, if we highlight the hydrogen from the HCl, okay, that hydrogen is now here, right? This chlorine is obviously here. Markovnikov addition. You need to know Markovnikov addition. Very important when you're an organic chemist. All right, naming these molecules here. The first two compounds I've drawn as these Lewis structures or partial Lewis structures. The last one is just a bond line structure. Well, there's a couple of ways that you can name the first compound, right? If you think about the biggest carbon chain as being the parent, what I have in the blue circle, that's a benzene. So if I number it like this, this could be called 1,3-dimethyl benzene. And technically, there's nothing wrong with that name at all, okay? However, when you have two methyl groups on an aromatic ring like this, we call those xylenes. So a xylene, and when they're in the meta positions or 1,3 substitution, we call that metaxylene. It's just a common name, and I did show you xylenes in the or xylene in the lecture slides. All right, the next one, the parent chain in the next one is also a benzene. Take a look here. The longest carbon chain is 6 carbons, so it's some kind of benzene. Now, what we want to do is we want to number these substituents in such a way that we give them the lowest possible numbers. I could start at the top, 1, 2, 3, 4. Then I have substituents at carbons 1, 3, and 4 on my aromatic ring. However, if I start down to the bottom, 1, 2, 3, 4, then I have substituents at 1, 2, and 3, 4. And if I compare 1, 2, and 4 versus 1, 3, and 4, okay, 1, 2, and 4 is going to win. So I've got a 1, 2 dibromo and a 4 tert butyl. Well, a bromo, Br, is going to come before Bu for a butyl. So this compound would be 1, 2 dibromo, 4 tert hyphen butyl benzene. Like that. We can take the exact same rationale for the last compound. I have 3 substituents. You might be wondering, well, which way do you number it, Mr. DeYoung? Do you start with the methyl group 1, 2, 3, or do you do it the other way around? Well, hold on. Before we do that, notice that we have a common molecule in here, right? This is a toluene, right? If we have just an aromatic ring with a methyl group on it, that is called toluene. So we can name this compound as a toluene. We assume that the carbon with the substituent is going to be carbon number 1. If this is 1, this is 2, and this is 3. So I have a 3 iota and a 2, 1, 2, 3, 4. A 2-butyl. So butyl, right, starts with B. Iodo starts with I. So B is going to come before I. So this is a 2-butyl. 3 iodo toluene. So you've always got to be on the lookout for common aromatic compounds, things like toluene, phenol, aniline, right? Compounds that came up a lot in Chemistry 102. All right, let's do another one. It says, write the condensed structural formula for 3-methyl-1-pentanol. Look, the easiest way to do these is to always start with a bond line structure and then work back from that. So if we have a 1-pentanol, 1, 2, 3, 4, 5, put the hydroxyl here. If we label these carbons 1, 2, 3, on the third carbon we have a methyl. Okay, there's a nice condensed structure, or sorry, a nice bond line structure. Now, how are we going to write a condensed structure for that? Let's see. Let's start with carbon number 1. We have a CH2, and carbon number 2 is also a CH2. So I can put those two in brackets like this and put the hydroxyl next to them in that way. After that, carbon number 3 is a CH. And what's attached to it? We have a methyl group, the CH3, and then we also have CH2, CH3. Now, obviously, you're not going to be asked to write these out in this way on your exam since it's a multiple choice exam, but you should be able to recognize a structure or put together a structure in your mind or on paper from a condensed structural formula. A little more nomenclature practice here.
Mr. Dion?
Yeah, go ahead.
Obviously, like you said, we're not going to be able to draw it like it said. So will there be questions that are like multiple choice? What will 3-methyl-1-pentyl look like?
Of course.
Okay, cool. Perfect.
Definitely,
thank you.
Everything's fair game. All right.
Okay,
Yeah.
I was just thinking.
Yeah, no worries. All right, let's take a look at some more nomenclature problems here. 4-methoxy-octanol. Technically, there shouldn't be a space here, but whatever. It's the land of the free. Let's see here. So if it's octanol, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. Al denotes that it's an aldehyde. Okay, so we'll put our aldehyde over here. Then if we number the carbons going 1, 2, 3, 4. On the fourth carbon, we have a methoxy. What's a methoxy group? It's when you have a methyl and an oxygen, right? We have methoxy, ethoxy, propoxy, isopropoxy, tertbutoxy, so on and so forth. And so if we have a methoxy, on that fourth carbon, we have the oxygen, and then we have a methyl group attached to it like that. Now, I don't like to mix condensed structures with bond line structures too much, so we'll draw it like that. That would be 4-methoxy-octanol. Next one is 3-methyl-2-pentanol. Again, I like to just start with the longest chain, 2-pentanol. So I have 5 carbons, 1, 2, 3, 4, 5. On the second carbon, I have my alcohol. Why don't I number them like this? 1, 2, 3, 4, 5. So on the second carbon, I'll put my hydroxyl group. So that's a 2-pentanol. And then on the third carbon, I have a methyl, just like that. I think that's a question that all my students could get pretty quick. The next one, we get another ether. Right, remember an ethoxy group. Ethoxy would be just like an ethyl group, except now you've got an oxygen attached to it. So we've got 2-ethoxybutane. Again, there shouldn't be a space here, but whatever. We got 1, 2, 3, 4 like this. On the second carbon, we have an oxygen. Then we have CH2, CH3 like that. 2-ethoxybutane. Not my most beautiful structure, but hey, gets the point across. All right. Oh, I like any question that has to do with intermolecular forces and solubility, that kind of stuff, because we spent a lot of time talking about this kind of thing. You know, which one of these compounds is going to be most soluble in water? Remember, like dissolves like. So if we're looking for something that's going to be soluble in water, it should have properties similar to water. I'll just draw the compounds out here kind of quickly. So we have 2 isopropyl hexane. So 1, 2, 3, 4, 5, 6. On the second carbon, we have an isopropyl like that. The next one is 2-tert-butyl 1-pentanol. So 1, 2, 3, 4. On the second carbon, we have a tert-butyl group like that. And what's the last one? Nonanal. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll draw our aldehyde like that. We can see that all of these compounds have a hydrophobic portion, don't they? Right? They all have some kind of big, non-polar portion, even the alcohol. However, the alcohol has the capability of hydrogen bonding, doesn't it? It can participate and it can donate a hydrogen bond. And so this one will be the most soluble. Now, it doesn't ask us which one would be the least soluble, but I want you to be very fast on this to be able to say, well, this carbon, or this compound rather, is a hydrocarbon, and so it would be the least soluble, right? There's no reason why a hydrocarbon would be soluble in water whatsoever, because hydrocarbons have no polar bonds, no capability of hydrogen bonding or dipoles or anything like that. Whereas a compound like nonanal is somewhere in the middle of the road, right? It does have a dipole in the molecule. However, because of this long carbon tail, it certainly won't be soluble in water. All right, even this compound's solubility in water would be limited, but it would be more soluble than the other ones. All right, next one. Draw a reaction that converts propene to isopropanol. Well, this is nothing more than testing your knowledge on if you had this molecule, which is propene, how would you convert that to isopropanol? What would you do? A Markovnikov addition, right? Because the rich would be the ones who get richer. You'd add the hydrogen over here, and then the hydroxyl would be added to the middle carbon. So what do you need to do that? You just need some acid and water. And if you don't want to write that, if you wrote H3O plus, that works. If you wrote, H2SO4 in water, they all are going to do the exact same thing. Okay, all you're denoting is that you've got acid and water. That's it. And that's another example of a Markovnikov addition. Nothing more than a good old Markovnikov addition. So you can see that it's pretty important, the Markovnikov addition. This is something that you were asked to do in one of your pre-labs, is draw an example of a hydrogen bond between ethanol and water. Well, you weren't asked to do it between ethanol and water, but it said represent hydrogen bonding. When you represent hydrogen bonding, so we'll just draw the water molecule like this. We've got a lone pair here and a lone pair there, and we'll draw the ethanol molecule like this, okay? The way that you do it properly is you should always put the delta minus by the oxygen and the delta plus by the hydrogen, right? Because that's where the polar bonds are. The oxygen is the second most electronegative element in the periodic table, therefore it's going to be partially negative, and it's going to suck electron density away from the hydrogen, which renders it partially positive. But then to represent the actual hydrogen bond, it should be between the lone pairs and the hydrogen like that. That's the proper way to represent a hydrogen bond. Now, what you drew might not look exactly like the way that I've done it, but it should be some kind of, facsimile, I guess. It should look something like that. All right. Which would be expected to undergo dehydration at the lowest temperature? A primary, secondary, or tertiary alcohol? I would never ask you this question. Now you might be saying, well, then why is it in your review? Because it still warrants a discussion. Something I want to talk to you about briefly. Let's say we had a primary alcohol. We'll have propanol. So this is primary. If we had a secondary alcohol, I chose 2-butanol. We could have chosen anything else. And then if we have a tertiary alcohol, okay, let's say we have this, okay? So this is 2-methyl 2-butanol. Well, which one of these is going to dehydrate to give you, or dehydrate at the lowest temperature? Basically what that's saying is which one of these is going to be dehydrated the easiest? The one that would be dehydrated the easiest is the one that's going to give you the most stable product, right? Whichever one's going to give you the most stable product, it's going to have the lowest activation energy. And the answer is the tertiary alcohol. Let me show you why. Because if you were to produce the Zaitsev product from this compound, if you treated this with H plus and heat, you would end up with this compound. Okay, that alkene, which is tri-substituted. If you were to try the same thing with this alcohol, you'd end up with, and I'm not going to draw the reaction, but you'd end up with this compound. And if you tried it here, you'd end up with this, right? This alkene is di-substituted, and this alkene is only mono-substituted. So it boils down to which alkene or which product is the most stable. So that's the kind of rationale you want to have in organic chemistry. Things should make some kind of sense. With that in mind, let's take a look at another question that involves dehydration. So drawing a Zaitsev and a Hoffman product. If you're still struggling with this, this is a good opportunity. We have the alpha carbon, which is the carbon the hydroxyl is attached to. I'm going to label this beta carbon in blue, and I'll label this beta carbon in red. Why do I have two different beta carbons? Because this carbon and this carbon are different, aren't they? Then one in red is a methylene, it's a CH2. The one in blue is a methyl, a CH3. If we were to remove the proton, the beta proton from the carbon I have highlighted in blue, I would get this compound. I would get one hexene. Whereas if I removed the carbon that I have highlighted in red, I would end up with this compound, 2-hexene. This is the Zaitsev product. Okay, did I write Zaitsev when I meant to write Hoffman? Sorry. This is the Zaitsev product, the most substituted, and this is the Hoffman product. Right? So this one is going to be the major product. Again, you look at the carbon-all-carbon. You look at the carbons next to it. If they're different, then you can get a dehydration from taking a proton from either of those carbons to produce the more substituted alkene, the Zaitsev product, and the less substituted alkene, which is the Hoffman product, which is the minor product. All right, circle a molecule that is expected to have the lowest boiling point and explain why. We've got 3-pentanone. Pentanone, 1-ethoxypropane. It's going to look, son of a gun, to look like this. It's 1-ethoxypropane, pentanal, this guy, and 1-pentanol. 1, 2, 3, 4, 5. There we go. The lowest boiling point. We spent a lot of time talking about ketones, aldehydes, carboxylic acids, alcohols, alkanes, and their boiling points. Can anybody suggest to me which one of these would have the lowest boiling point? And it's not a trick. Yeah, absolutely, Gavin. It's the ether. Yeah. So this one will have lowest boiling point because it has the weakest intermolecular forces. Right, we talked about this a lot. Now, this molecule, 1-pentanol, is going to have the strongest intermolecular forces, so it will have the highest boiling point. Why? Because it can participate in hydrogen bonding. If we compare the ketone and the aldehyde, it's actually difficult to tell the difference between those. They would have similar boiling points, but they have really strong dipoles because of the carbonyls. But the ether does have a dipole, but it is a weak dipole. And so since it's got a similar molar mass to pentanal and 3-pentanone, it's going to have the lowest boiling point of all. All right. Number 31, which of the following compounds will undergo oxidation with potassium dichromate to form a carboxylic acid? You don't even have to memorize the formula of potassium dichromate, which is K2Cr2O7, potassium dichromate. It's just a strong oxidizing agent. There's no way that we can oxidize this, is there? We can't oxidize a ketone. Ketones don't undergo oxidation. There are situations where they can, but it's not covered in our class. So A and C are both ketones. Ketone. And like I said, a ketone, when it's treated with an oxidizing agent, undergoes no reaction. Whereas an aldehyde when you treat that with a strong oxidizing agent, is going to undergo oxidation, isn't it? It undergoes oxidation to produce a carboxylic acid. And so the answer is B, the aldehyde will undergo oxidation. The two ketones will not. Explain why a ketone can't be oxidized. I think I had a question similar to this in one of the pre-labs. Why can't a ketone be oxidized? It's because it doesn't have an alpha hydrogen. Ketone does not possess an alpha hydrogen. Right? If we look at an aldehyde, for example, we do have an alpha hydrogen. Whereas if we look at a ketone, on the carbon there is no alpha hydrogen attached directly to it. Number 33, can 2,4-dimethyl-3-pentanone undergo keto-enol tautomerization? We spent a little bit of time talking about keto-enol tautomerization. If I draw this compound, 2,4-dimethyl-3-pentanone, in order for a ketone or an aldehyde to undergo keto-enol tautomerization, right? Remember that tautomers are just isomers that differ in the placement of a pi bond and a bond to hydrogen. In order for this compound to undergo tautomerization, it has to have, here's my alpha carbon, it has to have a proton on the beta carbon, and it has two beta protons. Okay, they're both identical because there's a plane of symmetry in the molecule, but at equilibrium, the compound will be mostly the ketone. However, I can rearrange the pi bond and have it here, and I can have that red hydrogen up here on the oxygen. And this is the enol, right? This is the ketone or keto form, and this is the enol. So keto-enol, and this process is called tautomerization. Tautomerization. All right, a good old hydrogenation reaction, right? The product or products from the reaction below. What's the name of this reaction? We're taking this molecule, which is 2-methyl-2-butene. It's not trans, it's not cis, because these two groups are identical. What are we doing? We're treating it with hydrogen and platinum catalyst. This is hydrogenation. Dangerous reaction if you're not careful. You're using hydrogen gas. And so what happens is you end up adding hydrogen atoms across that double bond, and you end up producing an alkane, which in this case would be 2-methyl-butane. Hydrogenation reaction. Very important reaction. We looked at it many times in this class. So make sure you are fully aware of the hydrogenation reaction. Draw the bond line structure of 2-methylpropyl butanoate. Oh boy. When I see butanoate, what does that mean? It means I'm dealing with an ester. The first part, the 2-methylpropyl, that comes from the alcohol. And the butanoate, that comes from the carboxylic acid. Now, obviously, these are just pieces that I'm referring to, right? Because when you make an ester, you take an alcohol, you combine it with a carboxylic acid, and you end up making an ester, plus you produce water as well. Okay, so the alcohol portion comes from 2-methylpropyl. So if I have 1, 2, 3 for my propyl, there's my oxygen. On the second carbon, I have a methyl. Good. Now the butanoate, I have the carbon from the carbonyl. It's going to have 4 carbons. 1, 2, 3, 4. So that would be 2-methylpropyl butanoate. Now that's an IUPAC name. You could also call that isobutyl. Butanoate would also be perfectly correct. Isobutyl butanoate. Nothing wrong with that. Butanoate. Or isobutyl butyrate even would work. Okay, name the following molecules. Well, the first one's a carboxylic acid. The longest chain of carbons has 1, 2, 3, 4, 5 carbons. So this is some kind of pentanoic acid. And we have an ethyl group at carbon 2. So this is 2-ethyl pentanoic acid. Now that's the IUPAC name or the systematic name. There is a common name for this. When you have 5 carbons, it's valeric acid. And you label this group as being alpha, right? You have alpha, beta, gamma, delta. So this would be alpha ethyl valeric acid, and that would be the systemic name or common name. No, that's, yeah, sorry, I'm losing it here. I'm like everybody else, just a little tired. So this would be the common name. IUPAC is the same as the systemic name. Okay, let's take a look at the next one. We have a compound that has 2 halogens on it. This one's kind of an interesting one. If you number from this end, 1, 2, 3, 4, 5, 6, you have substituents at carbons 2, 3, and 5. If you were to number starting over here, 1, 2, 3, 4, 5, right, then you'd have substituents at 1, or sorry, rather 2, 4, and 5. And so the red numbers are going to be the proper way of numbering it because we go for the first point of difference. We have a 2 bromo, we have a 3 iodo, and we have a 5 methyl. So if we list these in alphabetical order, the bromo is going to come first, the iodo will be second, and the methyl will be last. So if we slap all this together, we get 2 bromo, 3 iodo, 5 methyl hexane. Draw the line angle, which is the same thing as the bond line formula of hexadecanoic acid. Now, I know we didn't look at a lot of compounds longer than 10 carbons, but you can put this one together. You have decanoic acid, which has 10, and then you add 6 to it for hexa. So that means that we have a total of 16 carbons in the molecule. Let's give it the old college try. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And there you have it, my friend. That's it. Hexadecanoic acid. So this would be considered a fatty acid, wouldn't it? It's got this big hydrophobic tail over here, polar head group. There we go, a fatty acid. Number 38, which would you expect to have a higher melting temperature? Decanoic acid or cis-6-enoic acid? Can anybody take a guess on this one? Which one would have a higher melting temperature? Oops. Yeah, so this is the other compound. So this is cis-dec-6-enoic acid, right? This means that the double bond is on carbon 6 and that it's cis, right? You have the 2 hydrogens on the same side of the molecule like that, or the same side of the double bond, I should say. Can anybody guess which one of these would have a higher melting point? The decanoic acid or the other one? Well, if you think about them in terms, yeah, exactly, Gavin, I agree with you. It would be the decanoic acid, right? Because if we had a second molecule of it, right, if I just copy and paste it just for fun, so I'll paste it over here, you can see how this would pack together with another molecule of this very efficiently, right? They're going to fit on top of each other, and you're going to maximize the intermolecular forces between the 2 molecules. If I try the same exercise with this thing, if I copy and paste that guy, there's no way they're going to pack as efficiently, right? They just won't. Okay, so the packing is not going to be as efficient, and therefore the straight chain carboxylic acid is going to have the higher melting point, and it's because of increased surface area, greater contact of the two surfaces of two of the molecules. All right, let's move on to question 39. Draw the products of the acid hydrolysis of 2-methylpropyl ethanoate. We're kind of obsessed with these 2-methylpropyl groups. Anyhow, so 2-methylpropyl, remember this part comes from the alcohol portion, if you will, and this part comes from the carboxylic acid portion. Okay, so we have 2-methylpropyl. So we have our oxygen, and we have 1, 2, 3. There we go. So we have our 2-methylpropyl, and then we have ethanoate, right? So that means we're going to have 2 carbons in the carboxylic acid portion. 1, 2. There we go. 2-methylpropyl ethanoate. Now what happens if we hydrolyze this ester in acid? Here's our ester. We take it and we treat it with acid and we heat it up. Which bond is going to break? It's going to be the single carbon-oxygen bond, which would leave us with this left over and this left over. Well, if we're also adding H2O, we're going to have H2O, like that. So that's the alcohol that we end up with. And that is the acid that we end up with, acetic acid. Draw the products of the base hydrolysis of butyl acetate. Well, let's start by drawing butyl acetate. So butyl comes from 1, 2, 3, 4 carbons. Acetate comes from a carboxylic acid with 2 carbons. So there's my butyl acetate. Now, if I take this molecule and I put it in base, so I'll put hydroxide, and if I heat that up, this is a saponification reaction. We're going to break the carbon-oxygen single bond. We're going to end up with the alcohol. Maybe I should be careful about how I draw my hydrogens. I'll put it like this. But instead of ending up with a carboxylic acid, I end up with a carboxylate, right? Carboxylate, because saponification, right? We're in base, so we're not going to end up forming an acid in base. So those are the products you form in 39, whether you do saponification, and you have to know what saponification is, or if you do, this is just called the acid hydrolysis of an ester. Acid hydrolysis of an ester. All right, a little more nomenclature and drawing practice. Cis-1,2-diethyl cyclopentane. We're going to start by drawing a cyclopentane. 1, 2, 3, 4, 5. If we call these carbons 1 and 2, I have an ethyl on both of them, and they're both on the same face of the molecule. I can draw them both pointing up. If you want to draw it like this, that works. If you drew them both pointing down, that also works. They represent the same thing. What's the next one? Let's go to the one below it. 2-methylpropyl, 2-chloropropyl ether. So look, I've got some kind of ether, right? Remember the ethers, when you have 2 R groups attached to an oxygen. The first one is a 2-methylpropyl. So 1, 2, 3, 2-methylpropyl. The next one is 2-chloropropyl. 1, 2, 3, chloropropyl, like that. There we go. If I go to this one is just crazy. It's way too difficult. I would never ask this one. It's 5-bromo, 3-isopropyl trans hex-2-ene 2-thiol. So if I have 2-hexene or hex-2-ene, so I have 1, 2, 3, 4, 5, 6. My double bond is going to be like that. That's trans, the way it's written. On carbon 2, I have a thiol. 1, 2, 3, 4, 5. Here I have a bromo. And then on carbon 3, I have an isopropyl, like that. And you can see that the highest priority group on this side is on the opposite side of this group here. So that is trans, right? They're trans. Technically, that's not even a good name. That's actually a mistake. This should be it should be E, right? Because when groups are trans, they're supposed to be identical. So you can scratch this one. It's not my finest question. The next one I think is pretty reasonable. It's a bifunctional compound, but it's an amino acid. You've got 4 amino, 5 hydroxy octanoic acid. So look, if we have 8 carbons in octanoic acid, 1, 2, 3, 4, 5, oops. 1, 2, 3, 4, 5, 6, 7, 8. On carbon 4, we have an amino. 1, 2, 3, 4. So there's an amino group. On carbon 5, we have a hydroxy group, like that. So that's 4 amino, 5 hydroxy octanoic acid. All right. Industrially, we often need ethanoic acid, which again is the same thing as acetic acid, right? You need it to put in your vinegar, right? So industrially, we often need to make ethanoic acid. The starting material for this product is usually ethylene. So ethylene is just CH2 with a double bond. It's an alkene. Show a series of reactions that would transform ethene to ethanoic acid. Look, I'll never ask you this, okay? Not going to ask you this question. Not a big fan of this question, but I just want to talk through it with you. I think it's a good opportunity for a review, right? These are things that we've learned. What if you started out with ethylene? So there's the bond line structure of ethylene, and you treated this with acid and water. That would just do the addition of water across the double bond. So you would end up with ethanol, right? You go from ethylene to ethanol. Okay, well then what could you do with that? If you oxidize a primary alcohol with a strong oxidizing agent, what does it form? It forms a carboxylic acid. And so there's a 2-step process to go from ethylene to the alcohol and then finally to the carboxylic acid. What is saponification? We've gone over this already this evening. It is the basic hydrolysis of an ester. Okay, that's all it is. Right, if you take an ester like this, you treat it with hydroxide, what do you end up with? You end up with a carboxylate, and you end up with an alcohol. That's it, my friends. What type of biological molecules may include a hemiacetal? Where did we see a hemiacetal in a biological molecule? Can anybody tell me where? What chapter? We saw hemiacetals come up a bunch of times in one chapter. A bunch of times in one chapter. While you're thinking about it, I'm just going to go grab some water. Oops. All right, can anybody tell me where we would have seen hemiacetals come up? Yeah, absolutely. The carbohydrates chapter. Right? Oops. In the carbohydrates chapter. Carbohydrates. And we saw them in polysaccharides. Polysaccharides. Things like amylose. Okay. Things like cellulose. We saw that those molecules are held together by glycosidic bonds. Some more nomenclature. First one on the top left is a ketone. The parent would be cyclopentanone because we have a cyclopentane with a ketone, so cyclopentanone. If we number it like this, 1, 2, 3, this would be 3-methyl cyclopentanone. All right, the next one is some kind of cyclobutane. You have both bromines on the same side of the ring. So we have 1, 2, 3. So this would be a 1, 3, sorry, a cis 1, 3 dibromo cyclobutane, right? It's cyclobutane because we have 1, 2, 3, 4 carbons in the ring. The next one is an ester. We have an ethyl group over here. And since we only have one carbon over here, we could either call this methanoate. Could call this methanoate, or you could call it formate. Either one works. So you could call this ethyl methanoate, or you could call it ethyl formate. Either one is perfectly legit. The next one is an anhydride. The only anhydride that we looked at a lot in this class was this one, which comes from acetic acid. Right? If you take 2 molecules of acetic acid, 2 times acetic acid, and you heat it up really hard with acid, and you end up losing water, you end up forming this molecule, which is called acetic anhydride. Or you could also call it ethanoic anhydride. I don't know who in the right mind would do that. Ethanoic anhydride. If you've ever wondered, like, why do you say stuff like that? Why is it that nobody would ever say that? Why are some names normal? It's just because it's just the way chemists talk. Acetic anhydride is such a common reagent, comes up so often in organic chemistry that most people just use the common name all of the time. I would never use the IUPAC name or the systematic name of acetic anhydride. I just wouldn't do it. All right, this next one is a derivative of a common molecule that we looked at. Right, what I have in the yellow circle, right, this molecule here, when you have a benzene ring with a methoxy on it, we call this anisole. So if we call this carbon number 1, we could go 1, 2, 3, 4, 5, 6. So this would be, let me see, I'm kind of running out of space here. This would be 2, 6 diethyl anisole. And the last one is an amide. Amides are sometimes tricky, especially since this is a tertiary amide. You can see that you have 1, 2, 3 carbons in this chain over here. So this is some kind of propanamide or propionamide. Either one is fine. And we have 2 methyls on the nitrogen. So this is NN. Let me write this a little neater. NN dimethyl propanamide, or you could call it NN dimethyl propionamide. Either one would be perfectly reasonable as a name. So some more nomenclature. We spent a lot of time working on nomenclature. Well, let's get into some reactions here. It says draw a Lewis structure for each of the following functional groups. Draw a condensed structure too. Well, let's just draw some functional groups. If you have an alcohol, you should recognize an alcohol is looking like that. If you have an aldehyde, you have a carbonyl that has an R group on one side, a hydrogen on the other. If you have a carboxylic acid, right, you've got a carboxyl group attached to a R group. And then for an alkene, that's when we have a double bond, and we'll put 4 R groups on that. They can be the same or they can be different. So make sure you're aware of your functional groups before you come into the final exam, okay? Other functional groups that don't come up nearly as much, things like thiols, right? We spend a lot of time talking about thiols. Amides, right? You have to know an amide. Let's do it like that. What else? An ether. You should know an ether, and we already saw an ether this evening. You should know an ester, which is when you have a carbonyl and then another oxygen, then an R group. What else? Anhydride, acid chloride, alkyne, right? These are the kinds of things you need to know before coming into the exam. Okay, question 46. Rank the following molecules from lowest boiling point to highest boiling point. We're kind of obsessed with these boiling point problems. Hey, I just want to throw this out there to my students. Is there any one of these molecules that to you just looks like, yep, that's got the highest boiling point? If I call them, why don't I call them A, B, C, and D? That way you can describe it easier. Is there any one of these that kind of looks to you like, yep, that's going to be the king of the castle? What's the functional group that's in B? Yeah, B is an ether. Okay, C is an alcohol. So this is going to have the highest. So if we go from 1 will be highest, and we'll go down to 4, which will be the lowest. Okay, the alcohol is going to have the highest boiling point by far, right? The ether, we'll talk about that after. D is a ketone, and A is an ester. Now, we went over the reason why an ether has a lower boiling point than an aldehyde and a ketone this evening. When the three compounds that are difficult to tell apart in terms of their boiling points are aldehydes, ketones, and esters. Very difficult to tell them apart. Usually you kind of have to look, okay? So for the ester, if you put 2 or 3, and then here you put 2 or 3, I would grade that correct no matter what. So if you're wondering, are you going to ask me something ambiguous on the exam? No, of course not. But it's just easier, you know, to just say, okay, well, if you have an ester or ketone, it's very difficult to tell. You probably have to look it up most of the time. If you get enough experience, you might get some intuition, but I wouldn't stress about that too much. All right, let's see if we can name these molecules. Didn't give myself a lot of room to do that, did I? We take a look at A. It's ethyl acetate, isn't it? Right? We have this, and then we have, so this is ethyl acetate. If we look at B, it's that diethyl ether, right? Diethyl ether. You could use that to knock yourself out. What else? We have isopropanol or 2-propanol here. So that would be this compound. This is 2-propanol. And if you want to call it isopropanol, that's fine. Rubbing alcohol. And the last one, this is butanone. I did a lab the other day, not in this class, in a different class, and we were getting the students to identify some unknowns, and one of them was butanone. And I told them, you know, it's part of the flavoring found in microwave popcorn, and it's when you smell it concentrated, it doesn't smell like microwave popcorn at all. It smells terrible. But you can kind of understand, like when you get a whiff of it, like why, or you know, if it was much more dilute, why you could put it in microwave popcorn. Anyhow, kind of interesting. Draw an example of keto-enol tautomerization. Look, we've already gone over this a little bit tonight. I want you to be able to recognize when you have an enol and when you have a ketone. So the example that I put in the answers, the solutions, was just something like this. Let's do something different though. Let's say we had cyclohexanol, like that. Here's my alpha carbon, here's a beta carbon. So in the enol form, what you would do, let's label one of these beta protons in red like that. What happens is you end up still having a bond to your oxygen. Did I draw an alcohol when I meant to draw an ketone? I think I did. Okay, there we go. So we have our keto form. Sorry about that. Now what's going to happen is we're going to migrate that double bond. We're going to leave our oxygen here, but now the hydrogen has moved up here. Right? There still is the other hydrogen, right? That one is still here, but it didn't migrate. Okay, so that's the keto form, and then this would be the enol form. You need to know the difference between a ketone or a keto form and an enol form. Some more nomenclature. These ones are a little bit tough. I might skip these ones in the interest of time. Of course, you have the solutions posted to D2L, and you can take a look at those. These ones take a little more thought than some of the other ones, and I don't think I have anything, they're not really complex. They're just kind of a little bit annoying. Let's take a look at the first one. I call this one 3-ethyl 5-cyclopropyl 2-pentanol. So 1, 2, 3, 4, 5. On the second carbon, I'll put so this is 2-pentanol. Then on the third carbon, I put an ethyl group. And then on the fifth carbon, I put a cyclopropyl. So this is a cyclopropyl group like that. The next one is cis 6-methyl 3-heptanal. So look, you've got your aldehyde 1, 2, 3. 1, 2, 3, like that, and it's got to be cis. 1, 2, 3, 4, 5, 6, 7, like this. You get your aldehyde, cis. So 1, 2, 3, 4, 5. No, sorry. Let me number these. 1, 2, 3, 4, 5, 6, 7. There we go. So on the sixth carbon, you have a methyl group, and you know that this is cis because these two hydrogens are on the same side, like that. I guess, doable, but they're just a little bit long. The names are a little bit cumbersome. Let's see here. 2,5-heptadiene 4-ono jeepers. So look, you have heptadiene on 2 and 5. You have double bonds. So 1, 2, 3, 4, 5, 6, 7. Then you go 1, 2, 3, 4. So there's your 2,5-heptadiene 4-one. You have methyl groups on carbons 1, 2, 3, 4, 5, and 6. Also a little bit of a cumbersome molecule. The next one, cis 6-bromo 2,4-hexadienoic acid. We're going to skip that one because I'm not going to ask you anything that involved. Okay, and you can try it, of course. It's always good when you're practicing to go one step beyond, your comfort zone, and that will really help to push you. It's just like, how do you get to be a good weightlifter? Do you just lift the same weights your entire life? No, you pick up heavier weights and heavier weights. You make it tougher and tougher. Next thing you know, you look like Arnold. Okay. Anyhow,
Mr. Dion?
Yeah, go ahead.
Can you review letter B again?
Yeah. So
okay,
cis 6-methyl 3-heptanal. So you've got the ene like this. So this means that you have an alkene in the molecule, and the alkene is at carbon 3. So it's a 3-alkene. And the Al, that means that it's an aldehyde. So this compound has more than one functional group in it, right? So if you have 7 carbons, heptanal, right? 1, 2, 3, 4, 5, 6, 7, like that. Okay. So on the 7th carbon, there's your aldehyde. Now you number them. 1, 2, 3, 4, 5, 6, 7. On the 3rd carbon, you've got an alkene. So you put in that double bond like that. But the problem with the way that I have it drawn is that it's trans, right? The two hydrogens are on opposite faces like that. So what I do is I'm going to erase all of this spinach over here, okay? As neatly as I can. Okay, and then I'll make it into a cis. So 3, 4, 5, 6, 7. Now you see the two hydrogens are on the same side of the molecule, or the same side of the double bond, I should say. And then I also have a methyl group at carbon 6. So 1, 2, 3, 3, 4, 5, 6, 7. So I slap on a methyl group here. And now what I have drawn here in red is identical to this here. Okay, those two molecules are identical. Does that help?
So the cis applies to the number 3.
It applies to the double bond.
Oh, okay, that helps.
Right,
It applies to the double bond. Okay.
These two hydrogens, rather, those two hydrogens are cis. Right, they're on the same side of the double bond. Same thing here.
Yes, I see that. So just thinking, like, if I see this in a test, how will I know if I do the cis to the 6 or cis to the 3?
You know the difference between a cis and a trans, right?
Yes, I'm just wondering about the numbers.
Oh, yeah, yeah. Well, that you just kind of follow it piece by piece, right? So
Yeah.
since if you look at the name, okay. So where's my object? Go. So remember, the parent has 7 carbons in it. It's a 3-heptene al. So an aldehyde is always at carbon number 1. There's no other option. Right? An aldehyde always has to end the molecule. Always ends the molecule. So that tells you that this 3 represents the alkene. Right? Because the heptenal has 7 carbons, hept, but the aldehyde is going to be on the first carbon. Right? And then the rest is just the other part, the parent chain, just filling it out. Okay, let's see here. Draw the reaction of propanal with 2-propanol to create a hemiacetal. This is always a tough one for students. Not always. The students find this one challenging sometimes. So we'll start it with propanal. So here's propanal or propionaldehyde. We're going to react it with 2-propanol. And then what do? We treat it with acid, H+. Okay. And we end up forming a hemiacetal. So here's what we do. We're going to start by drawing the propanone molecule. However, we're not going to draw the double bond, right? Because what happens is the lone pairs on the oxygen are actually attracted to that carbon from the carbonyl, and they make a bond with it. So this part here, the alcohol, is going to be here. I have the oxygen, and then I have the isopropyl group like that. Where did this hydrogen go? It goes up here, and that is my hemiacetal. No, hemiacetal, like that. Okay? If I treat that with another molecule, and this isn't being asked of us, but if I treat it with another molecule of the alcohol, and I treat it with more acid, and I heat that up, and I end up losing water in the second step, I could form an acetal, which looks like this. I'd have, son of a gun, I'm running out of space. It would look like this. So I'll have 1, 2, 3 carbons. I have my oxygen with my isopropyl, another oxygen with another isopropyl, and that's it. There's my hydrogen. Right? This is an acetal. Remember, a hemiacetal is when you have a carbon that's got a hydroxyl and an ether on the same carbon. That's a hemiacetal. When you have an acetal, you have a carbon that has 2 ethers on the same carbon. All right. Why are carboxylic acids more acidic than alcohols? Well, if I take an alcohol like ethanol and I deprotonate it, I end up with ethoxide. If I take acetic acid, let's say, and I deprotonate it, then I end up with an acetate ion. Could anybody tell me what's the difference between these two? Why does the acid give up the proton more readily or preferentially? It's because you end up with a carboxylate that is what? It has enhanced stability on account of its resonance stabilization. So this conjugate base is resonance stabilized. Right? I have this resonance structure, and then I also have this resonance structure. Right? So since that electron density on the oxygen, the negative charge is delocalized over those 2 oxygens, it's stabilized, and that's why the conjugate base is more stable, so it more readily gives up a proton. All right, I'll move this just because it's kind of in the way. Draw the enantiomer of the following molecule. Remember that an enantiomer is a non-superimposable mirror image. There's a couple of ways you could draw this. You can either try to draw the reflection, or you can do it the easy way. You just draw the same molecule. Everything that's a wedge, you convert to a dash. Everything that's a dash, you convert to a wedge. So you have the hydroxyl here, and you have the proton here, and there you go, my friend. You've just drawn an enantiomer. An enantiomer. All right. Let's move on from there. Where are we? Question number 53. What requirements must a carbon have in order that it be designated or denoted as being chiral? The carbon atom must be attached to 4 different groups or atoms. Okay, so that gives you a chiral carbon. How many stereocenters are in the following compound? Might be a little tricky. You'd have to spend a little time on this. I'll help you out with this one. We have a chiral center here. This is not a chiral center, is it? Because we have a CH2, right? The carbon has 2 hydrogens that are attached to it, so it's not chiral. This is not a chiral center either. There's 2 methyl groups, so those are identical. This one is a chiral center here. And these ones are kind of tricky. I don't think I would ask these, but these 2 are chiral centers. We didn't talk about chiral centers on alkenes, so I'll just leave the 2 in red out. As long as you would be able to identify the ones that I have circled in blue, that would be perfectly acceptable to me. Next one, we're looking at some, these are technically aren't Fisher projections, are they? Because they show all the wedges and dashes, but they look like the precursor to Fisher projections, don't they? But it just says, which of the following pairs of stereoisomers are related as enantiomers? I'll give you a second to look at it and tell me if you can identify any pair of enantiomers here. Could anybody identify any pair of enantiomers here? Somebody says A and D. I'm not sure about A and D being enantiomers, but I would say that B, let's go with A. I would say that A and C are enantiomers. Right? A and C are mirror images of each other. Right? You have the nitrogen here, the nitrogen here, the hydrogen here, the hydrogen here. Right? So those are enantiomers of each other, these 2. And I would say that B and D would be mirror images too. So these are also enantiomers of each other, B and D, and then A and C. All right, progesterone, which is present in humans, is a single stereoisomer, has 6 stereocenters. How many possible stereocenters are there? Or stereoisomers are there? The number of possible stereoisomers, number of stereoisomers is equal to 2 to the power of n, where n is equal to the number of stereocenters. Stereocenters. This is something I didn't go over with you in class. It's not beyond the scope of our class, but I just wanted to share it with you. It's kind of interesting. So if you have a total of 6 stereocenters, then the number of possible stereoisomers would be 2 to the 6th power. So 2 times 2 times 2 times 2 times 2 times 2, which gives you a total of 64 possible stereoisomers. The reason I put that in here is you think about it, you got this cholesterol derivative, which has 6 stereoisomers, or 6 stereocenters rather, a possible 64 stereoisomers, and you only end up making 1 in the human body. It's pretty remarkable when you think about it. All right. Let's see here. It's 6:47.